When you finish this program, you will understand the operation of the VE pump, so you can relate to service and troubleshooting instructions. Some of you will repair or calibrate this pump on the test bench. Some of you will make minor pump adjustments on the vehicle. All of you will know what you're doing and why. Why is the VE pump important to you? This late model distributor type pump will be found in growing numbers in passenger cars, imported and built in the United States, in other applications such as light marine, small industrial, and agricultural. Yes, you'll be seeing more and more diesels and more VE pumps to service. What is a VE pump? The V comes from Verteiler, meaning distributor. It's also called a rotary pump. It's more compact than most familiar diesel injection pumps. The governor and supply pump are not external, they're inside the VE. The integral supply pump keeps the interior filled with diesel fuel, not lubricating oil, but fuel under pressure. We'll show that in orange. Under control of the pressure regulator, supply pump pressure rises with RPM to as much as 100 psi, about 7 bar. The VE pump can lift fuel directly from the tank through the filter. Some fuel bleeds through an overflow to carry away heat back to the tank. Like a spark ignition distributor, the diesel pump starts the power stroke with proper timing and distributes to each cylinder in firing order. In the VE pump, the single plunger operates with two motions, rotation and stroke. In the center of the distributor head, the rotating plunger distributes high-pressure fuel, shown in red, to one outlet passage every 90 degrees in this four-cylinder application. High pressures may average around 2,800 psi, about 200 bar. As the distributor slot lines up with each passage, it delivers high-pressure fuel from the center of the plunger. You'll find various models of VE pumps with distributor heads and outlets matching the number of engine cylinders. So distribution by rotation is one job of the plunger system. Fuel metering is another job. To understand fuel metering, let's look at the stroke motion. Plunger stroke is constant in the VE pump, but the rollers don't lift on the cam. It's really the other way around. As the plunger and cam plate rotate, they lift on the rollers and are returned by the springs. From bottom dead center, you can see the constant plunger stroke as cam plate and plunger lift on the rollers to top dead center. In our four-cylinder cam plate, there's a cam lobe lift within each 90-degree sector. If you consider the rollers as fixed, you can see the cam plate and plunger rise up on the rollers to TDC and return to BDC. Look again at the two motions of the plunger, stroke and rotation. You can see the plunger may dwell at BDC before and after the stroke, but even during the dwell, plunger rotation is continuous. That's important because during the rotation, the fill port lines up and opens one of the fill slots, bringing in fuel for one cylinder. The port then closes. We know that port closure is related to timing and metering of fuel delivery. Let's see how. Remember the motion of the plunger? Its stroke to TDC and return, and its continuous rotation? The plunger fills with supply pump fuel, shown in orange, during pre-stroke, while it's still at BDC. After rotation to port closure, the plunger lifts from BDC and begins delivery at high pressure, shown in red. The distributor slot delivers high-pressure fuel, through a delivery passage and line to each cylinder in firing order. There, the fuel injector needle opens and fuel is delivered. How does this delivery stop? That's the job of the metering sleeve. As the plunger strokes through the metering sleeve, the movement uncovers a spill port, opening the high-pressure circuit and spilling the remaining fuel into the pump interior. This is called port opening or spill. Effective stroke ends with port opening, even though plunger stroke continues. With the drop in pressure, the injector cuts off delivery, aided by its delivery valve at the pump distributor head. So for each plunger rotation and stroke, we have fill to port closure, delivery to port opening, and spill. For a 4-cylinder engine, we have 4 plunger strokes in 1 pump revolution, 360 degrees, which is, of course, 720 engine degrees. The VE pumps we've been discussing are called zero pre-stroke because port closure occurs by rotation before the plunger lifts from BDC. You can identify these pumps by the simple fill slots, which port close by rotation. Contrast the zero pre-stroke with the plunger of a different pump which has a pre-stroke. Because of this annulus or circular slot, the fill port cannot close by rotation alone. Instead, the plunger must lift for port closure. Only after the annulus lifts beyond the fill port do we have port closure. For this type of VE pump, lift to port closure settings are important because delivery does not begin until a specified lift from BDC. Regardless of port closure, port opening is determined by the position of the metering sleeve as the plunger and spill port move through it. The metering sleeve position determines the amount of fuel delivered. What positions this sleeve? It is usually the accelerator pedal, some form of power control lever. For low power, light accelerator pressure, the sleeve is closer to BDC, so the spill port opens sooner by plunger stroke. For greater power, the sleeve is farther from BDC, so the spill port does not open until later in the plunger stroke. So as this lever positions the sleeve, it determines the effective stroke. The effective stroke is always less than full plunger stroke. It is the spring and fly weights which determine the force on the governor lever and sleeve. When does the governor control? You may recall it controls at start, low idle, full load, rated speed, high idle, and overrun or coasting. For each case, let's see how. At startup, the fly weights are at rest, so the guide bushing is pushed back to the left in this picture. The governor lever pivots to move the metering sleeve the other way, away from BDC. Then how does that affect fuel delivery for startup? That's right, maximum delivery. At startup, spill occurs only after the plunger takes its longest stroke to port opening. When the metering sleeve is farthest from BDC, the effective stroke is longest. So for startup, the greatest quantity of fuel is delivered, greater even than at full load. Now, as the engine starts, the fly weights open out, moving the guide bushing to the right. So the governor lever pivots the sleeve to the left, shortening the effective stroke. With the sleeve close to BDC, the plunger moves only a minimum distance before the spill port opens. thus a minimum effective stroke. At low idle, the governor controls fuel injection at the idle RPM, tending to compensate for temperature and load changes. When you increase power, move from low idle to high-speed stop, what happens? Fuel delivery depends on a balance of forces, spring forces balancing flyweight forces, pivoting the lever to move the metering sleeve. When you're increasing power, spring force tends to move the sleeve away from BDC against the opposing flyweight force. The flyweights are collapsed at low RPM, and at full load, the spring force is greater than the flyweight force. The metering sleeve is moved away from BDC, so the effective stroke is longer. The fuel quantity per stroke is greater, the engine accelerates, and the vehicle gains speed. In part, speed is determined by load. Climbing a hill, full load may be at some partial speed between minimum and maximum. As the RPM approaches rated speed, what happens? At rated speed and full load, the spring force just balances the flyweight force, holding the metering sleeve for rated speed delivery. Full load continues at rated speed, but no more. Now, suppose you run the engine at no load, as with the clutch down and accelerator full down, holding the control lever against the high idle or maximum RPM stop. At high RPM, the flyweights move out, opposing the spring. The flyweight force is stronger, so through the lever, it moves the metering sleeve to reduce effective stroke. This reduced fuel flow is called high idle. Notice this no-load condition produces a maximum RPM faster than rated speed, but at a fraction of the fuel delivery. Finally, suppose you release the accelerator and coast, returning the governor lever to the low idle stop. What happens? At high RPM, with accelerator at idle, the flyweight force overcomes the relaxed spring. The metering sleeve moves so close to BDC that injection pressure never develops, a zero delivery condition. Zero, because the metering sleeve is so close to BDC that it never covers the spill port during the plunger stroke. Zero delivery during overrun is one reason diesels are so economical during conditions such as city driving. You've seen that at full load, the governor lever moves the metering sleeve far from BDC. How can we make a full load adjustment, say to increase our full load fuel quantity? On the governor, you'll find a full load adjustment screw. You should adjust this screw only on the test bench, never on the vehicle. This screw adjusts a special lever called the correction lever, pivoting at point 1. Notice this correction lever carries pivot 2, the normal pivot point you've seen for spring and flyweight force on the metering sleeve. So moving this full load adjustment screw shifts pivot 2, which has the effect of shifting the metering sleeve and so changing our full load delivery. On the test bench, you can turn this screw to move the correction lever inside the pump. This movement, in to increase, pivots the correction lever at pivot 1 to move pivot 2 and the metering sleeve, increasing the effective stroke and therefore the full load fuel delivery. You can see why this full load fuel delivery must be adjusted before the other settings. High and low idle can be done on the test bench or on the vehicle. In the shop, set idle RPM at the low idle stop. Set maximum RPM at the high idle stop, but leave the full load adjustment screw alone. You've seen distribution and metering in the VE pump. We'll conclude with injection timing, the timing mechanisms, and the timing adjustments. In a procedure similar to spark timing, diesel injection timing is adjusted to the engine by rotating the pump housing around the drive shaft axis. Timing is set by turning the pump in the mounting bolt slots so injection begins at the correct time. In this cutaway VE pump, you can see the timing device, the timing piston and its opposing spring. At low RPM, supply pump pressure has little effect on timing piston travel. As pressure rises with increasing RPM, piston movement advances the roller ring opposite to drive shaft rotation. This advances the time when the cam plate will lift from BDC to begin the stroke. So as supply pump pressure increases with RPM, the timing piston travels, advancing the time when injection begins. For this reason, procedures on the test bench include measuring the travel of the timing piston as the RPM changes. On some VE pumps, a cold start lever and cam advance the timing a few degrees, tending to reduce startup smoke. On most pumps, fuel shutoff is electrical. A solenoid valve closes the supply of fuel to the fill port and the plunger. You may find a mechanical shutoff. The lever system overrides the governor spring to move the metering sleeve to zero delivery. You've seen the compact VE pump pressurized by the integral supply pump, the single plunger rotating for distribution of fuel to the cylinders in firing order. You've seen the meter delivery to port opening and spill, the metering sleeve opening the spill port sooner for lower power requirements or set to open later for greater power. Positioned by the accelerator, spring forces, and governor flyweights, governed for correct delivery quantity at various load and RPM conditions. Finally, you've seen the timing and the timing piston travel. Operating principles important to your service and troubleshooting instruction. Brought to you by BOSCH.